We're going to continue in this presentation, expanding kind of the traditional definition of hybrid simulation. We're really going to get into a whole other domain of physics. It's going to be with building performance simulation in respect to daylighting. So I know it's starting to get later in the workshop, so we're not going to get into the physics too much. We're just going to stay pretty high level, but I think you're still going to see it's a very obvious application for hybrid simulation. So just a quick background about myself. I did my bachelor's at University of Michigan in structural engineering, so I feel real comfortable on you guys. And then I came here to Berkeley. I got a master's and PhDs through the systems program that's in the civil department as well. I've been postdocing here at Pier since December of 2017. So I want to talk to you today about buildings, and specifically daylighting in buildings, and I just want to put up this kind of abstract depiction of kind of the system that we're talking about. So you can imagine here we have an outside and an inside, and they're separated by this building envelope, or you might have heard them referred to as facades, right? And so we can think about modeling this kind of a system with respect to how the daylighting is going to impact the interior of the space. So you can think like the windows and how the light is going to be coming in. And if you were a person in that space, what would you be experiencing, right? So if you were an architect and you were trying to attempt this design problem, there'd be a lot of things you'd be concerned about. For instance, glare. We've all been in buildings before where it's like, oh, I can't even see what's going on, or not enough daylighting in the space, and you have to have a lot of interior electric lighting. So that's kind of the design question and the modeling question that we're going to be approaching today. So first off, let's just take a very trivial case where you have just a glass facade, right? We've all been in a building like that, and it's just windows. In the industry, kind of architecture, they call that a glazing facade. It just means glass. It's a fancy word for glass. So in terms of modeling this, we actually have some really good numerical tools for that. It's straightforward. It's a program called Radiance, and there's a handful of other ones in the field, but Radiance is by far the industry standard when it comes to this. It uses a ray tracing model to simulate the light going through the glass all the way from your sun and your sky and your environment, and then you can calculate a whole host of metrics within the space. For instance, luminance, illuminance, different renderings, all sorts of different things. And they're pretty accurate. Actually, you can accurately model more than your eye can actually see. You're below that threshold. So they're good. But the problem starts to come in is when you have not easy transmission through the facade element, okay? So this starts to become a problem with non-speculars, how you call that. So you can think about a ray of light going in and then kind of a fan of light coming out, right? Or maybe even have multiple reflections going through that building envelope. So they call that a complex fenestration system, so a CFS. You can think about CFSs. Here's some examples where you can think about them. You might see them around. So commercial examples that are already out there are fritted glass, basically where they print different semi-transparent materials on regular glass. You can think about frosted glass with different types of finishing or even different types of just printings on the side. Something we've done some work here is with translucent concrete panels. So you have like different optical fibers embedded in opaque concrete panels. And then these types of concentrators, we call those compound parabolic concentrators. So you can imagine that the physics of the light is no longer just cutting right through. It's no longer this transmission in the specular. You're starting to get these different, more complex behaviors. So you might say, well, I see a lot of these windows around. I don't see a lot of these windows around. Why don't we just use Radiance, and be able to handle all these? But Radiance can't handle any of these complex fenestration systems, right? And beyond that, it's not part of the innovation, right? So you might say, well, again, I'm not seeing these around, but let me try to motivate that we're on the cusp of a change in the way that building facades are going to be made. So the green movement right now is targeting at reducing our energy usage throughout society, right? Buildings currently use about 40% of all the energy use in kind of developed economies. So within the buildings, the building envelope actually dictates a lot of the energy use. And again, there's a pretty detailed explanation of why that's the case, but we're just going to take my word for it that the building enclosure is an area where a lot of research is happening right now to try to reduce energy use in buildings. And a key area of that is complex fenestration systems. So as I said, we're on the verge of an explosion of innovative complex fenestration systems coming. So you can think about nanomaterials that are going to be affecting the way that the waves are being absorbed in the glass, the way what waves are going through, what waves aren't. 3D printing is beginning to come into the construction industry, and it's really changing the way what's possible to put on buildings, what's not possible. And then finally, dynamic facades that are actually changing their properties based on control. So, for example, electrochromatic windows, or even physical shading that is different geometries that you can manipulate to actually kind of augment the light that's going through. So you can see now, if we look back at our abstract kind of representation here, the building envelope now, we're right on the cusp of it no longer being easy to simulate, right? And so the idea there is, with this hybrid simulation technique now, can we reapproach this problem and try to measure certain physics, right, instead of trying to model them? So we can look at the building like this. You have a physical domain and a cyber domain. And what we're going to do is we're going to actually use physical excitation, so you can think like sunlight, to excite physical facade panels. Then we're going to measure those responses and then model the interior of the space using computer programming. So if we actually look kind of at the theory of the physical domain, we're just going to go real quick through this. So you can see there's the outside and the inside. And if you were to look at like a kind of an element of the facade, there's this input hemisphere that defines all the angles that light can strike the outside. And then there's this output hemisphere on the inside of the building. On the outside, you have sunlight exciting it, which is going to have two components, direct and indirect. And then on the inside, you have the luminance distribution function, which is this L, which is a function of theta and phi, right? So depending on what direction inside the space, there's light being transferred into it. So this is kind of a three-dimensional representation of what that looks like. You have the outside light coming in there from the sun, and then it gets input into the interior of the space. So when it comes to actually trying to realize this, right, because remember, this is in the physical domain, we need to ask the question, like, how are we actually going to measure this? And that's where we come into the cube, which is this kind of monstrosity here you're seeing up there. And I'll go through that with a demo in a second. But basically what we have here is, you can think about it as like a big camera. There's an aperture here, and then you have this hemisphere here with all these optical fibers. And these optical fibers are bending the light around. So you can think about it as like a discrete sampling of this hemisphere. And then they bend the light around to a two-dimensional plane. So those are the ends of all the optical fibers. And that's right here. Then you have in this area a camera that's taking a picture of the end of those optical fibers. So each measurement of the light at the end of the optical fiber corresponds to the amount of light that's exiting. So that's that L function, that's a theta, that's a function of theta and phi, right? So now that we have this physical measurement, what are we going to do with it? Well, we're going to plug that into our cyber model, or our analytical model, or our numerical model, however we want to call it. And we're going to do that in Radiance, because once you're in the space and you're dealing with just specular reflections around a room, we've got that handled really well. And so this is based on the central radiance equation, and we can talk about that if you're interested, but it's just a recursive triple integral or double integral that you solve, and that's not anything new. So we've got that really under control. So in terms of the actual model that we're going to be using, we actually have at our disposal now the full expressiveness of radiance, which is any geometry you can imagine. But we're going to stick with the standard office model, which is a common model used in the daylighting community. It was developed by kind of the god of the daylighting, Christoph Reinhardt. He's a professor at MIT. And basically what it is it's just a rectangular footprint, and it has 6 desks in it with one area for glazing. Or in our case, we're going to put complex fenestration in there. So this is what we're actually going to measure then. We're going to measure the horizontal illuminance, which is basically the amount of light falling on a horizontal surface, at 0.8 meters, which is called the work plane height. So again, this is a standard kind of daylighting metric that's calculated. So we're going to calculate horizontal illuminance at a grid of points across that plane. So now we have the cyber domain calculated, right? Because we're going to use that input L, and we're going to run it through the simulation, and we're going to have the actual lighting distribution within the space. So now, if it's just a traditional facade that doesn't have any dynamic component, that's it, and we can go from there. But a lot of facades now actually are able to close the loop on these. So we have, within this cube specimen here, we have a couple different outputs so we can control. So you have like analog to digital I/O, basically pins on a DAC. We can do PWM with those. We can do like I2C with those. Basically, any type of protocol you can imagine, we can do that. For the purpose of this experiment today, it's just a very simple like bang-bang controller, which means kind of on-off, right? So we're going to be representing a shade that you would draw across the window. So you can imagine if it gets too bright, you can just draw the shade across the window. So the next thing to think about is kind of back in the physical domain is how are we actually going to excite this thing? And kind of the excitation mode or excitation sources now come in two main types. There's either natural, which is the actual sun, or we have artificial, which are like daylight simulators. So you can imagine this is truly a different type of physics, right? It's not an actuator or like the earth moving or an impact. It's actually electromagnetic radiation is our excitation. So it's this different type of physics that we're measuring here. So we're going to go in the demo here today. We're going to have a live demonstration, and we're going to do an artificial sun. So I'll show you this is a light. And in terms of what we're actually going to try to do here, we're going to model just a simple glazed panel. And then if the light gets too bright, we're going to have a shade deploy. And that's going to be based just on a very simple control law of looking at the actual horizontal illuminance that's calculated at the working plane. So if the working plane gets too bright, the shades are going to automatically deploy, and then when it gets less bright, they're going to retract. And again, this is just kind of a little bit of a contrived example to show you guys what was kind of the cutting edge of what we're working on. A different example might be some kind of geometrical changing facade, or something where you can apply a voltage and it changes the transmission properties. But with this, we're ready to go on the demo. So I'm just going to show you what's going to happen over here. This is the cube. This represents the glazing condition. Often when you're modeling or measuring glazing, kind of at this level, you don't actually have anything at all. And then this right here is going to display in a moment when the code starts running the actual illuminance on that working plane surface. So we'll just get it started and we'll go from there. So it should be showing up. Okay, so you can see there, we're kind of at a very low lighting situation right now. So the floor plan looks very, very dark. But as we move up, you can see it's starting to get lighter and lighter. And eventually, we're going to overcome the threshold of what the control law has, and our window's going to shut. So you can see now the light's a lot less, yeah. So you can imagine maybe that was it's backing off now, maybe there's a big cloud coming over. And so the light's, a little bit less, and so the controller now says, well, it's not as bright, so we can open the windows back up, right? And maybe it comes back. And it shuts again, right? And then now maybe that's the end of the day, and so the sun's setting, and so we're gonna back down, and you want to see those evening views, so the window opens back up. So you can imagine, the potential for a lot of these kind of scenarios really kind of explodes, and you get a lot of potential experiments that you can do. And so again, this is just a high-level demonstration. There's a ton of physics that is going on underneath it, and there's a lot that we can go on back and forth, because they're actually still discovering, fundamental physics with respect to light all over the world. So this is a great application where it's like, hey, the modeling is crazy, the systems are getting extremely complex. Like, let's measure it. Let's just use hybrid simulation, and we can get a great solution to these kind of problems. So with that, thank you again for your time, and if you have any questions, we can go over those, or we can wait till later. Thank you. Thank you.